This is the last in our series of videos on integrated rates. In part 4 of this series, we will show an example that uses integrated rate equations to solve a problem. Let's look at the following problem. The kinetics of the reaction of N2O5 gas decomposing to form NO3 gas and NO2 gas were studied experimentally at 100 degrees Celsius. After the data was taken, it was shown that a plot of the natural log of the concentration of N2O5 versus time was the most linear plot, and this plot had a slope of negative 0.00783 per second. The question has 4 parts. Write the rate law for the reaction and determine the value of the rate constant. Find the half-life of the reaction. Determine what the rate of the reaction would be if the concentration of N2O5 is 0.25 molar. And finally, a question that asks us to find the concentration or the amount of N2O5 at some later time. Let's start with part A. Write the rate law for the reaction and determine the value of the rate constant. Since a plot of natural log of concentration versus time was determined to be the most linear, this tells us that the reaction is first order in concentration of N2O5. So we can immediately write the rate law. Rate is going to be equal to K times the concentration of N2O5. And again, since it's first order, this will be raised to the first power. We also know that the slope of the plot was negative 0.00783 inverse seconds. Looking back at our table for the integrated rate equations, we see that a plot of natural log of concentration versus time should give a slope that has a value of negative k. So we can find the value of k by just taking the negative value of the slope. In this case, we'll then have 0.00783 inverse seconds as the value of our rate constant. What's the half-life of this reaction? If you go back to the video on half-life, we saw that half-life for a first-order reaction is equal to the natural log of 2 divided by the rate constant. If we plug in these values into our calculator, we get a result of 88.5 seconds. That means that every 88.5 seconds, the amount of N2O5 will decrease by half. Let's look at question C. Question C asks what would the rate of the reaction be if the concentration of N2O5 is 0.25 molar. Since we're asking for what the rate of reaction would be, we need the regular rate law. We've already seen that for this reaction, we have a first order rate law, where rate is equal to K times the concentration of N2O5 raised to the first power. We've also seen that the rate constant K is equal to 0.00783 inverse seconds. If we plug in the value of 0.25 molar as our concentration of N2O5, we find that the rate is going to be equal to 1.96 times 10 to the minus 3 molar per second. We want to round this to two significant figures, so we'll report it as 2.0 times 10 to the minus 3 molar per second. Let's look at the final question. This one asks, if a 1-liter flask was filled with 5 grams of N2O5 at 100 degrees Celsius, what mass of N2O5 would be left after 2 minutes? Since this question is basically asking for how much N2O5 there will be at a later time, we know that we're going to need the integrated rate equation, because that's the one that relates concentration at some later time to time. Since we've already discovered that this reaction follows first-order kinetics, we're going to start with the first-order integrated rate equation. Let's write that out. The natural log of N2O5 at some later time t is equal to the natural log of the initial concentration of N2O5 minus KT. I'm going to bring both natural log terms to one side. Combine them. Remember, because we're dealing with logs, when we subtract two terms, both natural log, we can do it as the natural log of that fraction. And now if I raise both sides, if I do the inverse natural log of both sides, I get the concentration of N2O5 at some time t over the initial concentration of N2O5 is going to be equal to e to the minus kt. Multiplying both sides by N2O5 initial concentration, we get the N2O5 concentration at some time t is equal to the initial concentration of N2O5 times e to the minus kt. We now need to figure out the initial concentration of N2O5. We know that we're starting with 5 grams of N2O5. If we multiply this by the molar, well, actually divide by the molar mass of N2O5, we can convert the grams of N2O5 to moles of N2O5. Dividing that by the total volume of 1 liter gives us our initial concentration of N2O5 to be 0.0463 molar. Now we can plug in and solve for the concentration of N2O5 at 2 minutes. We'll put in our initial concentration of N2O5, e to the minus kt. Remember that k is 0.00783 inverse seconds. Time is 2 minutes, but we need to convert that to seconds. 2 minutes is the same as 120 seconds. And we plug all of that into our calculator. We get that the concentration of N2O5 after 2 minutes is 0.0181 molar. The question actually asks for how many grams of N2O5 that is. So if we take our 0.0181 moles of N2O5 per liter, multiply by the fact that we have 1 liter, and then also multiply by the molar mass of N2O5. We end up with 1.95 grams of N2O5 as our final answer.